So this is a very important topic, you can imagine. Chemical fields are very ubiquitous. That's right. Is this ubiquitous? Very general in many biological situations. So we are going to cover gradients and chemical fields in detail here. First of all, I want to remind me that I need to record locally. Oh no, it's already recording. Okay. You can get the exercises done on your email. Probably Hayden sent you an email with the exercises done, zipped files, or you can go to the drive, students material, and find my exercises there. Okay. Also, I'm sorry for my English. I don't use my English every day. I'm still in Brazil. Never went outside, so my English is not as good as I wanted. And besides that, if you are an advanced student, if you already know how to use CompuCell, during the exercises, you can do the challenges that I'm going to offer you to do instead of the exercise, if the exercises are too easy for you. Okay. So let's go. The topics in this lecture are first fields and concentration fields. Then we are going to cover different types of transport of those fields, for example, advection, diffusion, and how diffusion is affected in biology situations. Also, the diffusion equation itself, its spreading behavior, because the diffusion equation basically models a spreading behavior of stuff in space. Also, how real tissues modify the diffusion equation, how field objects are built in CompuCell3D, diffusion solvers for those fields in CompuCell, also boundary conditions. It's very important for when you're using fields. And we are going to build the linear gradient, which is one of the very basic types of field that you may need in your simulations. Okay, so first of all, I want to ask you something, a very basic question. Let's see how you guys understand diffusion. So the question is that when you mix sugar in your coffee, for example, what is the basic physical principle behind the mixture? What do you think? The basic physical phenomenon that drives mixing sugar in coffee. Okay, but going from a piece of sugar, a piece of something in water, it will dissolve, yes, but what drives the mixing? Entropy change, diffusion, passive diffusion, movement of particles. Okay, movement of particles, you need movement of particles, but which type of movement? Hydration spheres. Okay, but how do they move? Concentration gradients. Okay, we will see. First of all, let me describe a little bit what a field is. So fields can be of many kinds. So in CompuCell, we are treating specifically about real, scalar, classical fields. Okay, your fields can be non-classical, non-real, non-scalar, but this is not the topic. The thing is, the most common field in CompuCell in biological things are the concentration fields. And what is concentration? Concentration is basically the density of a distribution of particles that you use to not need to track each one of the particles. You calculate a density for each piece of your Physically move with spoon. This is actually is the best answer so far. Okay, but we will cover this. So concentration is basically the density of the particles in space, but you can have fields which are not from particles, from distribution of particles, molecules, etc. For example, temperature fields, or of course, gravitational fields, electrical fields, many types of fields. And there is a non-scalar field in CompuCell, which is the vectorial field. And there is another one, which is the tensorial field. So if you have many cells with shapes, different shapes in the space, you can define, this is not built in, okay, we will not cover this, I'm just citing because it's interesting, tensorial field for the inertia tensor of the cells, okay? So hopefully this video answers the question I gave to you. This is dye, he's putting dye on a bottle full of water, and seems like the dye is frozen inside the bottle. He even shakes the bottle up and down and nothing changes. If you look, seems like a frozen, but when he moves in the other direction, everything mixes up. This is because in this situation here, actually the dye is diffusing. It is diffusing, but you cannot see because diffusion is so slow. For you to mix something in a macroscopic scale like this, you need advection. You need to grab your spoon and mix the sugar inside the coffee. So a J is the best one so far, okay? Here in the left, we have a picture of a fluid flow carrying a distribution of a concentration, for example. So fluid flow changes the concentration of a field. In CompuCell, the cells will not carry the fields, will not cause advection in fields because the field lattice is different. So this interaction don't happen. And we are not going to cover advection in detail here. And not every field will suffer from advection. For example, gravitational fields won't suffer from advection. And there's a very interesting question I put here as well. Why in epithelium, for example, we can neglect advection from our fields, let's say oxygen field? Why we can neglect advection in epithelium? Let's say what you answer. So going to the diffusion. Diffusion is spontaneous, okay? But what is happening below the microscopic phenomenon? Below the microscopic phenomenon, we basically what's happening is the particles are colliding with the other particles of the medium. Perfectly, Sharon got it correct. The other particles are colliding with, let's say, the protein, and the protein undergoes a random motion and starts diffusing through space, okay? Because diffusion is this spreading, right, behavior, diffusion will happen from high concentration to low concentration regions, and many types of fields can diffuse. For example, mass, charge, and energy densities, all of them behave like diffusion, like spreading, okay? Like I said, like Sharon said, actually, epithelium is a barrier, so spatial configuration affects how field diffuses. And here is another video that I put, very interesting. You have a difference in temperature. So because temperature is what drives the strength of the collisions in the microscopic scale, you will have faster diffusion in the right cup. But here you also have advection, and temperature also affects advection, because when you have the hot cup is cooling by the walls, and it will generate advection. So this is also very, very misleading to say to give as an example of diffusion. In biology, because diffusion is a spontaneous process, it is very, very cheap for the cells to use diffusion instead of some active transport to move proteins and small ions, for example, around the cell, because a cell is a short thing, most of the cases. Diffusion, it will be a very good option for transport. But as I said, since diffusion is the result of many random collisions in a particle, the particle will not will not displace in a straight line. It will randomly diffuse in a random fashion. So the displacement, the total displacement, won't be proportional to the time, to the time variation. It will be actually proportional to the square root of the time. So if you invert this relation, the time it takes for a particle to displace a certain amount of space is proportional to the square of the length displaced. Okay, so in this example here, if a molecule takes 1 second to displace 1 micrometer, for example, it will take on average 4 seconds to displace 2 micrometers, and so on. I gave an example, a real-life example. In a G-actin molecule, inside a cell, it takes about 1 minute to travel the entire cell from membrane to membrane, okay? Supposing the cell is round. So the diffusion equation is like this. Phi or phi, the Greek letter, represents a field. This field can be concentration, can be temperature, so I put 2 examples here. Also here we have the differentials, we have a temporal derivative, we have a double spatial derivative. No, we are talking inside the cell from membrane to membrane. It would be cubed. Yes, maybe. Yes, probably. So I got it wrong. Sorry. Spreading behavior of diffusing fields. So why does the diffusion equation models this spreading behavior? Well, this is mathematics, but basically the proportionality between the concentration variation to its curvature, it's what makes the peaks flatten and the valleys go up. So the peaks go down, the valleys go up, everything flatten. So the tendency of the system is always homogeneity with no curvature, flat. Okay, so this is a very nice example extracted from the channel 3 Blue and Brown. So I recommend very much you watch this video here. I put in the reference if you want to understand deeply what the diffusion equation is. And obviously the diffusion coefficient here is constant through time, through space. So if the diffusion in your system is not constant through space, this equation will not hold. This equation will be different. So be aware of this. Also, tissues will modify how fields behave, for example, simply because of obstacle. But there's another type of phenomenon that can occur, for example, binding. So those particles can bind to those obstacles instead of just colliding. And there's another one still. The particles can traverse the membrane, can cross the membrane inside one of those obstacles and not get out anymore. Okay? So there are many ways of disturbing diffusion in real tissues. In CompuCell, we are gonna talk about real scalar fields representing concentrations, and those fields are defined in a lattice, in an extra lattice, let's say, equal to the cell lattice, but they overlap each other. They don't interact, they overlap. So you solve in the same mathematical situation as the cell lattice, but one is superposed to the other. Okay. We also have the vectorial fields, but we are not covering this in this workshop because it is limited. But you can define your own vector fields using multiple scalar fields, one for each component of your vector field. Okay. About the diffusion solvers now. So the diffusion solvers are the methods, the mathematical methods to solve the diffusion equation in your system, in the lattice. Okay. So the first one is the fastest one is the steady state diffusion solver. Yeah, I don't know how to answer this question, Barrett. So the steady state diffusion solver is the fastest one, but it doesn't model the transient between the initial condition to the steady state. So when will I use the steady state diffusion solver? When my biological process is much, much slower compared to the diffusion of my field. So when my biological system does one set of actions, my field, I know that my field already spread to its steady state, already settled down. So in this type of cases, I will use a steady state diffusion solver. Okay, it's very, very fast. The diffusion solver FE is the most common. In general, we choose this one because it models the transient between the initial condition and the steady state. So, for example, your biological system is moving, and because it's moving, it's affecting the field, and then you need the field to move around, let's say, to diffuse again, so you reproduce some biological process in the way. The reaction, I almost forgot. You can solve with diffusion solver FE using GPU, but you need a compatible GPU and proper syntax for that. But I never used GPU version, okay, so this is not my expertise. You also can set different diffusion coefficients for different cell types, and also different decay coefficients for different cell types. And the last one, also a very important one, reaction diffusion solver, in which you have, for example, more than one field, and you are modeling a coupling between those fields. Let's say one field generating the other. Okay, generating, I mean one field decaying and the other growing, for example, or both reaching an equilibrium in a certain region of space. So to model some simple reactions, you can use the reaction diffusion solver FE. The most stable is the diffusion solver FE, so that's why we choose it by default. Okay, but you can check the specifications for all solvers in the documentation. The reference is here.
We have a good question here, Pedro. Does FE in these solvers stand for finite element?
I don't know, Hayden. You ask. Yes, okay.
I'm not sure either, but yes, I would assume so. Okay, yeah, it looks like yes, it is finite element. So it is using the finite element method to solve.
If I can jump in here real quick, I'm not sure what FE stands for. James might know, but the diffusion solvers use central difference method. Yeah, finite element is too computationally expensive to be doing this much solving. We do, however, have a finite volume method solver in the works.
Thank you, TJ.
Thank you, TJ, as always.
No problem.
And I almost forgot as well, diffusion solver, not the steady one, the diffusion solver FE is expensive computationally, so don't use it too much. Like, let's say many 20 fields. No, calm down. Okay, it's very expensive computationally. It will slow down your simulations.
Pedro, I think I might have lost your audio.
Oh my God, I was muted.
Yeah, only for the last 30 seconds or so.
Okay, okay, sure. So when setting up a new simulation, you will see this window here where you set the name of your field, choose the diffusion solver for your field, hit add, always don't forget to hit add, and you can repeat this process for as many fields as you have. Then simply press next and end your simulation. In the XML file, you will find this piece of code, the steppables with the name of the diffusion solver, where you can set the diffusion constant, the global diffusion constant for your field. Later, we will see that you can set individual diffusion constants for each type of cell. Also, same thing for decay. And here you are seeing initial, it's commented a line, initial concentration expression, X times Y. So here in this line, you can set your initial concentration using mathematical expressions. So you can do basically whatever you want. And there's also another way to create initial conditions, which is by uploading a file. So here you just specify the file path. So if you want, for example, to start your simulation from a very, very complex field that you measured in an experiment, you can upload your file, specify the file path here. And also you can do this in Python if XML is limited to what you are trying to do. Another very important thing is the boundary conditions. So how... Yes, the system has boundary condition. I'm covering this right now. So basically the field will interact with the boundaries, the walls of the lattice, and we need to specify how this interaction happens. For example, a periodic boundary condition is when something disappears from an edge and appears in the other, in the opposite edge. So for example, if you are trying to simulate an infinite system, this is a proper boundary condition for you. We also have a constant flux, which is the same as constant derivative, where you have a flux, an influx or outflux of your field in the barrier, in the boundary, by a fixed amount. And you also can hold on the boundary a constant value. So the value of the field in this place, in the boundary, will also be a certain value that you choose before the simulation. There is another type of boundary which is not implemented as a built-in function still in CompuCell, which is the Fickian boundary, which is basically a flux, but the flux is proportional to the concentration different before and after the boundary. So there is a way to do this in CompuCell, but you have to do this by programming, coding, which will define a membrane, and then the field will flow through the membrane. And because you set a specific diffusion coefficient for this membrane specifically, you will have the Fickian boundaries. So, but it's not implemented as built-in function. So now I have an exercise for you to, let's say, make sure you understand how those boundary conditions can be used in real biological situations when modeling those biological situations. So the first situation is an epithelium. The epithelium ends at some point, okay? At least that's what I'm seeing here. And it also has another barrier below the layer of cells. And it continues forever in those other, let's say, boundaries of our lattice, of our simulation, okay? So which boundary condition would you choose for each one of those sites? In the case of an epithelium. What do you mean top, bottom, cell, cell? I don't understand this. Periodic along X, okay. periodic in one direction, which direction? Non-periodic in the other, but so it makes a tube. Non-periodic, but which one? In the other direction. And we will specify the same boundary condition for the end of the epithelium and the bottom. Is it the same? So you have a barrier here that separates the epithelium from the I don't know the words in English for this case here. It's the endo what? Periodic to prevent what? I might be on a different page. Okay, so probably you're using the endothelium. Okay, so you have the endothelium below this separation. There's a I don't remember the name of this layer here, this barrier here. Keep the signaling within the cells. Okay. Basal layer, yes, basal layer. Yes. So in x-axis, I will give the answer. Okay. This is 3D. No, for now this is 2D. But could be 3D, so you would have another axis. So I think Barrett is right. I actually, yes, Barrett is right. So periodic along X. So you are basically here, you are trying to model an infinite layer. So when you go to the right, on the right boundary here, you expect to see more epithelium. So one way of doing this is to connect the right side with the left side. So we will apply periodic boundary conditions in x-axis. Okay. In the case where we don't have anything above, I saw blood vessel and two, and was thinking, okay, we are going to the second one briefly. Because you don't have anything above the epithelium, here a proper boundary condition would be a constant flux 0, because you don't lose chemicals to the medium and you don't absorb, at least for some types of field. Obviously, epithelium can change some types of fields, but for example, if you are modeling, for example, glucose field, I would choose constant flux 0 in the upper boundary condition, because you don't lose glucose to the medium and you don't absorb, at least probably you absorb, but if you don't have glucose on the medium, you won't absorb any glucose. So for a simple case, I would choose flux 0, so constant derivative 0 for the upper boundary. And for the basal layer, what would you choose? So you can think, for example, that the endothelium is providing nutrients, for example, or is holding a constant amount of nutrients that start diffusing towards the epithelium. So you could choose, for example, constant value fixed at some amount, and this amount given by the field concentration in the endothelium below the basal layer. So for the second one, I think I don't have time to cover everything in detail, but when you are modeling, for example, when your boundary condition should be a blood vessel wall, okay, the blood vessel wall, a proper boundary condition for it would be a constant value, because the blood is running and constantly exchanging nutrients. So it always stays at a certain value. Of course, in simple cases, okay? Being simple here. And the last one, let's say you have a layer of cells and those cells are secreting some fields, let's say whatever. What is a proper boundary condition for secreting cells in a membrane? In a membrane, no, in a layer, in a wall of cells. The cells are secreting fields. What is the proper boundary condition for this? Constant value, but if you put constant value, Megan, the cells will secrete up to a certain point. And if the field is above this certain point, the cells will start to absorb to reach that certain point again. So I don't think constant value is the proper boundary condition. Negative values, constant value inside the cell. Yes, but what if the field outside the cell is bigger? Because if the field outside the cell is bigger than inside, the cell will actually absorb. But no, the cell is secreting. So how do you make the cell keep secreting even though the field outside is bigger than inside? Constant flux, exactly. Constant flux above zero, okay? Above zero, please. Come on, above zero. Not zero, not negative, okay? So this was the exercise. So how do you set the boundary conditions in XML? So you will receive a piece of code. So it would be secreting, yes, exactly, Megan. You will receive this piece of code, and in this piece of code here, inside the steppables with the name of the diffusion solver, you will find many options. For example, you can set periodic, you can set constant derivative, which is the flux. In the minimum value of the coordinate, you are setting the boundary, and in the maximum position as well, you can set constant value as well for minimum and maximum. And the periodic, you cannot set, for example, periodic left and constant value right, because to set periodic, you need to have both. You are necessarily linking both boundaries together, okay? Linking both boundaries together, okay? But this is not the code you will receive when you start simulation into edit. Actually, when you start a new simulation into edit with fields, you always have to fix your boundary conditions because they will be set up in a very strange way. So don't remember, always when you set up a new simulation with fields, you have to fix your boundary conditions in this piece of code here, okay? I will show you later. And what you can do, right, with boundary conditions, one thing we can do, very, very simple, one of the most simple thing we can do is a linear gradient. So basically to do the linear gradient, you need to set a concentration in the x equals 0, for example, if we want a gradient along the x-axis, and another concentration at x equals L. For example, if your lattice has L, the x dimension is L. So C1 at x equals 0 and C2 for x equals L. So in this case, it doesn't depend of the initial state. Your field will always reach a steady state, a straight line between value C1 and C2, and they will be described by this equation, which is the solution, basically the solution to the field equation for this type of boundary condition, okay? So we are gonna do it, but for the guys that are more advanced, or the girls, right? I know many people that attended the course last year, so probably they already know how to set fields. So I have a challenge for them, and the challenge is this one over here. No tips, because it's a challenge. And you just need to build some type of field art in 3D using isosurfaces. So I hope this is a challenge for you, okay, for those that find the exercises too easy, okay, and me and the rest will go step by step through the exercises. Are boundary conditions set initially for the whole file in which the simulations are taking place, or also for compartments? No, not for compartments within. No. Yes, file. I understood the overall question. So no, it's only for boundaries themselves. Okay, so this is the exercise. So what we need to do in this exercise is basically set a constant concentration for x equals 0. So for the minimum x, and another concentration for the maximum x. And we will let the field diffuse and see how it achieves the steady state, which is dictated by this function, this solution here. Okay, and then we are going to plot this graph, the field values along the x coordinate, plot this graph and see how the shape of the field changes in space and in time. Okay, so let me first. So I will go through this step by step. Okay, so first thing, in the wizard, we will specify an initial condition, a uniform diffusion coefficient everywhere. Okay, so we won't bother with obstacles, etc. We will not use decay for now. Okay, then we are gonna set the proper boundary conditions and set the initial concentration as well. So we will go through everything I previously mentioned. So come with me. So CC3D project, new project. Then you give your simulation a name. For example, Pedro is nice. Next. So here you can reduce the lattice dimension if you want the simulation to run faster. I will leave as it is because it is simpler. Then here in the cell specification, we don't want any cell. So next, here in the chemical fields, we are gonna first set a name for our field. Let's say oxygen. Select diffusion solver FE and press add. So make sure you see your field specified in the table. Are you with me, guys?
Wait, does that say oxygen? I just can't
Should
quite
say.
see the screen.
Should say oxygen, yes.
Okay.
I'm sorry, I don't know how to make the font bigger. I don't know even if it's possible, I don't think so. But yes, oxygen, diffusion solver, FE. I pressed add, okay? Did you add cells? No. No cells. Let's keep it simple here for now. Okay, so you are with me apparently. So no cell properties because we don't have cell. Yes, right? Do you agree? Okay. First things first, for some reason, when you don't specify cell, even if you don't specify cell, there is a uniform initializer in the end of the XML file. So what we are gonna do is comment it out or delete those lines. And make sure you don't delete the 80 line, which is the bar CompuCell3D line. Don't delete this line, don't comment it. Okay, just comment the uniform initializer from steppable to steppable. Are you done? Done. Need more time, okay. If you need help, unmute and talk. Who needs more time? Do you need help?
Wait, how do you add a comment? Or how do you comment out the whole block?
Oh yeah. Yes, forgot. In to edit, you can comment selecting the lines and pressing Control bar. Oh, not this way. So must be Control bar and the right bar, okay? The right bar. Okay, like this. So it works for a single line. as
Pull
you were
down the
seeing.
edit command. Select and pull down edit.
Yes, you can also do this. Edit in the menu and block comment, block and comment option here, which also says the command that I use, which is very handy.
So one thing you have to watch out for in XML is don't comment a comment. That causes a syntax error. So if you're going to do a block comment, select things that are not comments initially. The newest version of CompuCell, the comments are supposed to work for commenting comments, but there's an oddity in the way comments are done in XML. That means that if you put a comment inside of a comment in XML, it's an illegal syntax.
Yes.
Okay.
So I
And
recommend
it's just this bottom block from 69 to 79, not
Yes.
not the top of the middle block.
Yes, not the top and not the bottom. Leave CompuCell3D alive, otherwise it will crash. Okay, so now I will suppose everyone is with me. So the next step is to set proper.
I think you uncommented yours. Yours is not commented, the code.
Yes, thank you very much. Thank you very much. Yes. So you can go now to the steppable diffusion solver. It will always appear with the name of the diffusion solver you are using. So around line 31, please go to line 31. You also have the name of your field 2 times. Okay, it is set 2 times. And global diffusion constant and global decay constant in lines 37, 38. So you can leave the global diffusion constant 0.1 and set the decay to 0 because we don't want to enter this already. Then in the boundary condition, see how it's messed up. Okay, so you have constant value 10 and 5. And you have constant derivative 10 and 5 for y coordinate. So it is very strange. Okay, always remember that you have to change those boundary conditions when setting up a new simulation. In our case, we want to set the x boundary condition to be 10 in the minimum and 0 in the maximum. So we build a gradient from 10 to 0. Okay. And then for the y-axis, you can set to build the linear gradient, you can set both periodic condition or constant derivative 0. So for simplicity, I will set the periodic boundary condition for y-axis. It is simpler, okay? So I will share a little bit more of my to edit here and make sure you have your XML file just like mine. And to those that are building the 3D challenge, no, I want to give a tip. It's a challenge. What am I doing? No tips. So if you want help, type in the chat or dismute and ask. What it means. So what it means, okay? So here. I will launch here my board. Some people say it's Paint. Okay, I say it's board, Pedro's board. So we have, for example, I will represent a lattice here. So you have your lattice and you have your X coordinate, okay? And you have your Y coordinate here, okay? So when you say X equals 0 or X minimum, what you are saying is this point here. Okay, so all points that have X equals 0, what are we talking about? We are talking about all this barrier here, this wall here. And when you say X maximum or X equals L here, you are talking about this point. So it is this entire wall here on the right. When you're talking about Y coordinate, Y equals 0 means this bottom wall here, and Y equals L, for example, is this entire wall here. So I hope I responded.
So we only had to modify the X axis. We didn't modify anything on the Y axis under the periodic.
We did modify. We changed it from constant derivative to periodic.
Where?
Look here, a line. Look to my tweet here. So X is Y. You have line 62 set to periodic. Okay, so here I have periodic. And those two lines that were uncommented, I commented, and they were the constant derivative lines. So we changed it from constant derivative to periodic. Okay. Yes, Megan. Yes, it would be the derivative. The derivative is the rate of change. Yes, per Monte Carlo step. Is the rate of change the periodicity? Probably someone can answer, not me. If we put constant value with numbers for X instead of I don't know. This I don't know. This I don't know. It is a very interesting question though. So probably the others can answer. I don't know this one. Okay, so I am moving on. I think we are done here. And we can launch our simulation. I press with the right mouse, open in player. Exactly, Sharon. Constant derivative to 0, Sharon. The best way to interpret it is a perfect wall, Sharon. So let's say your field is a temperature field, as an example. What is a perfect wall? A perfect wall is a wall that doesn't allow the field to change. So it would be an isolated wall. Okay, so if you have an isolated, insulated, I don't know how you say, isolated, insulated wall on your house, a perfect one, you can model using constant derivative 0. Insulated, okay. And if your wall is not a perfect wall, you will set a constant derivative below 0, negative, because then you are losing heat to the material. Okay? And this would be a Fickian boundary condition, actually. Because the external medium, the outside of the house, is in another temperature. And your wall is a membrane, let's say. So I am running the simulation here. I hope everyone is seeing something like I am seeing here. My code is not working for me. So Megan needs help. Yes, someone join breakout room with Megan, please. And what can we do once we set our field and our field is running here? How can we change, for example, configurations? So first, you open your configuration. And probably you are not seeing what I'm seeing here, because my configurations are different. I forgot to change in order to be equal to yours. So go to in configurations, you go to field, okay, and in the field tab, you
Pedro,
will see.
we have about
Yes.
5 people in the chat saying they're having similar issues with the code. We should probably stop for a second and back up.
Make sure cell field is set to oxygen. Not working, saying my code is not working. Make sure. Huh?
How do we
It's not
get to
looking the
that
same.
field tab? How do we navigate? It's just I can't quite see because of the screen, so I apologize for that, but I don't know how to navigate to this field part.
Is the slide too small for you?
Yes.
I will make a quick fix here. So I apologize. Okay. I will make it bigger. So I will talk over the words. Sorry, you need to see this, okay? You need to see this. Oh no, this is the preference. Sorry. Field here. Sorry, some so what we have here when in the field tab is first the range of of the field values that will appear in the heat map. So in the heat map, you can set blue will be 0 and red will be, for example, 10. So I will put here for you guys to see. So configurations field, you can set fixed to 10. in the maximum coordinate. Okay. Maximum coordinate, no, sorry. As the maximum value for the field. And 0 for the minimum value. Okay, so here you can change the scale of the heat map. Let me see the.
So we can only access this toolbar if our image populates, essentially, like if our graphic appears. So if our graphic does not, for whatever reason, we wouldn't be able to access these additional fields.
Sorry, so I think, Pedro, go into graphic 0 window and show how to select oxygen instead of the cell field.
Okay. So building another simulation, you mean?
Just no,
Ah,
don't
here.
just yes, that's what the issue.
Okay, sorry, I jumped this step here. Sorry. So you probably are seeing this here, black lattice. So what you will need to do is go here in there's some options in your window, in your graphics window. You can choose to see 3D, XY, XZ planes, YZ. You can also change the coordinate you are looking, the coordinate of the slice. And in the right, you have options of what you want to see. So for example, if you want to see your cells, you select cell field. If you want to see your oxygen field, you select oxygen. So I'm sorry, I didn't notice this detail. I'm so used to it that I missed it. I will launch the poll to see how you guys are doing. Actually doing, not making. Need help. One person need help.
I think 2 people need help. Gilberto, could you go into a breakout room with the people who need help, please?
Yes, I can.
So people who need help, please join the breakout room that is called, I think we have Gilberto.
Three people. Yes.
Actually, do I have one? No, I don't have one called Gilberto. Let me use the yes, there is one. There's a breakout room called Gilberto Tomas. Please join that room.
Okay, so we can move on now.
Does anybody else? I see Louise joined. Does Megan need to join? Norma? Sarana? If you need help, please join the breakout room labeled as Gilberto. Does anybody else need help now? Okay. Pedro, I think maybe if you can give people an exercise so that the breakout people don't lose too much, that would be good.
Okay, so can I just finish showing the options?
Please go ahead. Yes, please go ahead.
Okay. So you can set the range of the heat map scale. So for example, 1 to 10 fixed. You can also leave it unfixed, free, to choose what is the maximum value for you. So for example, as the example, fixed both minimum and maximum 0 and 10, as we have a linear gradient from 0 and 10. And in the output, there's nothing to do. That's all. And you can also check scalar contours to produce the ISO to get the ISO surfaces in case you are doing the challenge. And I just gave a tip. I wasn't supposed to. Okay, I hit OK. It takes a time, but now you can see that my my field is going from 0 to 10. Okay. And it takes a good while to settle down and achieve the steady state. So for this kind of simulation, of course, here we want to just to show with diffusing. But if you want to achieve the steady state really, really fast, you would choose the other one, the steady state diffusion. So, oh, here is the slide to show the oxygen. Okay. So moving on, now we want to plot the graph of the X field values and see how this graph changes over time. So to do this, we need to open our code. So I will close the CC3D. Open our code, go to steppables, and here we want to implement a plotting window, a plot window. So how do we do this? You have done this many times, but I will. Do I do the step by step here, James?
I've asked for a show of hands who would like to done step by step and who would like to try on their own.
Sorry.
Who would like to see it done step by step?
Okay.
Why don't you just go through it? It's okay. Go through it step by step. It's fine.
Okay. So step by step, let's go. CC3D Python on the menu. Then you go to scientific plots and choose the setup. And you must do this in the start function, okay? So if the code fell outside the start function, grab and drag inside the start function, okay? So I will get a little bit more space here with to edit. Here you can change the title, for example, field. You can also get my exercise done as well in the students materials demos, students materials demos, and exercise 224. Okay. Okay, so in the slide, there are other things. So I'm just setting up here the plot. I changed the title, changed the title coordinates, so not big deal so far. Now I will delete this 21 line because we only need one line, okay, for the field. And I will call it, let's say, F field. Why not? Okay, and I will leave the rest as it is. So now let's jump to the step function, and I will repeat the same process. So go to CC3D Python, now scientific plots, and add data points in the step function. So 2 lines spawned. Let's delete one of them because we don't need, we just need 1 line. And we will plot, the name of this plot is field, okay? So this name here must match this name here. From the add plot and the add data point must match the names here, okay? Now we need to add this point for each X coordinate. So we must loop over X coordinates. So in range, my lattice has 256 pixels. So this is the dimension of my lattice. And now we need to get the field value. Okay, how do we do this? So on the slide, what do we need to do? First, we need to specify our field, get the field reference. So in order to do this, we create a variable called field and reference it to the CompuCell field using the syntax self dot field dot field name, in this case, oxygen. You can get this code from the menu here as well. Scientific plots and no, sorry, chemical field manipulation and get field reference. It will pop the same line, but with a generic name. Okay, so you set this up on start function. Or not, should it be on step? Now I don't remember. Or should it have a self here? Now I don't remember. Well, I will see. Sorry. And now we want to get the field value, okay, for this coordinate, for each x coordinate. So in order to do this, we use another syntax, which is field, and then the coordinates we have. So for example, the concentration, let's get the concentration here. It will be equal to the field. It is the object that we get from the reference, and then you specify the coordinates. So in this case, x, then you can choose wherever a y position you want, because they will be all the same, and 0 for the z component. So x, whatever, 0. Okay. Just make sure you don't go below or above the lattice coordinates. So no negative values and no values above your dimension, your lattice dimension. And now we want to plot this concentration. So go here and change this cell volume to concentration. And we don't want to plot for different Monte Carlo steps. We want to plot for x coordinates. Okay, we are looping over x coordinate, and for each x coordinate we plot a concentration point on the graph. Okay. And we also need to clear the graph each Monte Carlo step. If we don't do this, our graph will become a mess. So CC3D Python, scientific plots, and erase plot inside the step function as well. And make sure this line is put before the loop. Okay. If you end the loop and then erase all data, you won't have any point on the graph. Okay, so erase before building the graph. Come on, please. What else? I think I'm done. So this can give me a mistake since I am defining a field in the start function, not in the step, but I'm not sure. I will test this now. Open and play. So let's hope. Field is not defined. So yes, I was right. This is a mistake. You need to reference your field inside the function you are using the field. Okay, so this should be obvious for me. Apparently, it is not. Now it should work. Yes, now it's working. Okay, it is working. So the field should resemble what we see on the heat map. So let's tile windows. I don't like this way timing, but I would like one up and one down, but okay, that's okay. So now we can see our field diffusing. Okay, and I have 15 minutes left. Yes.
Sorry. So we have a range of 256. So aren't you supposed to get 256?
Yes. Range 256. Python always go to the n-1 when you use a range function. So 256, the range will stop at 255.
Yeah, 25.
I must have done something wrong. I have a vertical line in my graph. Oh, I know what you've done. I know. I know because I done the same mistake one day. So probably your mistake is here in the plot when add data point. You need to specify x coordinate and the concentration. And this add data point must be in the loop that sweeps, I don't know if it's correct word, all the x values, okay? And then you plot x concentration, x concentration, x concentration for all values of x. Okay, probably this was your mistake. Is medium a cell type? Yes. If so, does it behave the same way as cells oxygen? No, oxygen is a field, not a cell, or whatever specified chemical in the heat map field, or is the medium special? The field is a cell, it is a special cell. Medium doesn't, you cannot access medium as you access cells, for example. Cell.volume works for all cell types except for medium. So if your cell is medium, you cannot use cell.volume, for example. So it is a special cell, but it is a cell. Oxygen, in our case here, oxygen is a field, it's not a cell. Okay, and a field is not a cell type. Okay, it's another layer superposed. Okay, yep, that was it. Nice. Your final code should look like mine. And as I said, it takes long to reach the steady state. So you should wait 25,000 steps to reach something like a linear gradient. Okay. Now for the exercise 2.2.2. We were doing the exercise 2.2.3. Now we are on the 2. Okay, so I'm sorry for that. It was when I was doing the slides. It was a mistake. But one thing I want to show you is the initial concentration here. We didn't cover this. So I will uncomment the initial concentration, leave everything equal, okay, everything normal, and put a different initial concentration expression. What are we gonna get with this? So leave this x times y. What does it mean? I don't know. Let's see. So I will hit stop and run. Look, so very strange here. Initial condition, and now my heat map ranges are not so good. So what I need to do is that I will simply unfix, okay, and see what it gives me, because I don't know what values we are 7,000 we are working. So this was the initial concentration set by that expression, and then we run. We start seeing it diffusing here. So you can put whatever expression you want in that initial concentration. So for example, that initial condition is very interesting. Maximum between 0 and a full strange expression. Let's see what it gives. So I will copy and paste this expression on the chat, but let me first assign it here. So it is maximum between what? Between 0 and 10 minus open parenthesis, open parenthesis again. So this is x minus 100, this is y minus 100. There is a plus sign here, and this one is squared, and this one is also squared. If it's not squared, we're gonna get negative values, okay? Is this? Yes. Yes, okay. So if I run this guy, what does it give? Gives an error, obviously. Yeah, sure. Why not? Maybe another parenthesis. Yes, parenthesis missing. Is it equal now? 2 parentheses here, 2 parentheses there. So it should work now. Okay, so now there is a dot. This strange dot here at the coordinates 100 to 100. This 100 is what we set here on the arguments, okay? So we generated a dot. And this dot starts diffusing and it dies. So I will fix the values here again. I'll fix to 1 to show exactly this point in space. Okay, so this is like a drop. This is like a drop of dye, okay, in our medium, and it starts diffusing. Okay, spreading out. It's a peak going down. Okay, and this other initial condition sets a boundary, an initial boundary, because maximum between 0 and 5 plus x defines a value for x between 0 and 5. So you can specify, this is a way to specify boundaries, initial boundaries for a lattice, okay? And this is what I use to do the challenge. So now I will show you the, I don't have the challenge here done. I have to download. But I will show you the challenge because I think it's interesting. So demos, module 2.2, and challenge. I'll put here on the simulations, extract. Okay, so now I will open that simulation. Where are you? Here. Where is it? Ah, here. Okay. So I set a very strange initial condition for the challenge, and as it runs, it eventually forms that surface that you saw on the challenge. And to generate this type of structure here, I went to configurations and I activated the scalar contours. These are the ISO values, and I set specific ISO values to build the layers that I wanted for this specific field. And the initial condition that I set to this guy here, let me go Find it. Where is it? Yeah. I have to open this on with it, sorry. Simulation. We're almost done, 4 minutes. Let me just show you the initial condition that I set. So first of all, I needed to add another axis, so z-axis for the challenge because the field is 3D now. So I basically copy and paste one of those lines, put right on z in one of them. I put constant derivative 0 in all of them, so I get those nice right angles between the isosurface and the boundaries. So this is why I chose constant derivative 0. And my initial concentration was this function here, which is basically a 1/x, but for all components. So in 3D, it gets this nice shape here. But you can create whatever surface you like. Let me write a random one. So for example, x minus x minus 10, y minus 10. I have to turn on my light actually. And z minus 10, for example. And obviously, because we don't want anything below 0, let's square everything. And we should get another interesting surface. Let's see. This is the other simulation. 2 minutes left. Look, another interesting thing. Okay, so it's 40. So here must be 20, not 10. So now it will be symmetric. Yes, haha, there we go. And as it diffuses, you'll see that the boundaries impose the right angles. Then we get those nice shapes. Okay, guys, that's it. That's it for my lecture. How do we describe?
Please
image?
run the poll, the module poll.
Oh, yes, sure. Questionnaire up and pull. Did the previous one take screenshots?
I launched it.
Okay. I wasn't
Please
sure.
fill out the poll.
Does the chat appears on the streaming?
No.
Okay.
No, just your shared screen with your video in the upper right.
So I don't know how to describe that image. I mean, it's a mathematically described image. So you actually describe by that initial function, and
So,
then yes.
What I was just going to say is, Sarana, that was an example of the field art that we introduced as the challenge for people who maybe already knew how to do fields. There wasn't any particular biological meaning behind that. It was just an exercise in constructing an interesting geometrical field.
Okay. I wasn't quite sure because it's like sometimes, it's always nice we generate these neat things, but interpreting them and making them meaningful to our audience isn't always
Right.
there. So I didn't realize it was just an exercise. So thanks.
Yeah, don't worry. There wasn't supposed to be something comprehensible there that you were missing. It was just a cool
Probably this
picture.
was a mistake, but the point is that you can do many things with fields. That's the point. So you can set up various types of initial conditions in your 3D field as well. And the challenge incorporates the 3D, the other component, the Z component. So this was the entire point of the challenge. So how to build fields in 3D, set the isosurfaces, and create something like there's no point of creating a specific shape, a specific, but obviously this has many applications in models. If you want a 3D field in a 3D simulation and setting up your own initial condition. So that's the point of the exercise, the challenge actually.